So now we're going to discuss Newman projections, and I'm going to attempt a new type of filming. So please bear with me with this because this is a lot to manage on my end. Okay, so the first thing that we're going to talk about is what ethane looks like. So notice here that I have ethane drawn, okay, right here. And I have it drawn so that the hydrogens go in the same direction. So that's what this would look like as to what you see there, okay? So we have two that are in the back that are in the same place, two that are in the front that are in the same place, and then two that are going down that are in the same place. And notice that I have an eyesight going from this direction, right? So if we're going to look at what's called a Newman projection, what we're looking at is not from this perspective, but rather from this perspective. And when we do that, you can see that we've got stuff that's in the front and stuff that's in the back. Now, notice that since we've drawn it like this, these two are basically in the same plane. These two are as well. You can see how as I rotate there. And then the two down here are as well. Okay, that is what we call the eclipsed conformation. So they are eclipsed with one another when we look down from this perspective. And you got to put something in the back or in the front so that you get them a little bit offset there. So that's the reason why you see them sort of offset there. I may not be able to get them exactly like that, but that's why. Now we could instead take this and rotate it slightly like we have here, okay? So notice that I just moved my hydrogens. So that is now looking at this formation right there, okay? Here we have one set of, let me make sure it's in the right place. Let me get that perfect for you all so I don't confuse anybody. One set that is going back and forth, and then this is going down, versus here, this one's going up, and then we have another set going back and forth. So if I again look this way, I go and look like this, okay? Now notice here, when I do it this way, I have hydrogen coming down in the front and two going off to the sides. And in the back, I have one sticking up. Oh, you can't see that. Sorry about that. And then one going off to each side as well. So maybe you can see that now. So in the front, we have those that are in red going down and to each side. And in the back, we have one coming up and down to each side. We refer to this as the staggered conformation. Okay, so we have an eclipse conformation and we have a staggered conformation. And if we just keep one of those still, we could start rotating the other one. So I'm going to keep the one in the front still and start to rotate the stuff in the back. And we can see that we can go from an eclipse conformation to a staggered conformation to an eclipse conformation to a staggered conformation, and it just keeps going back and forth. Okay, so when we have here is we have different types of energy levels that can occur, right? We can have a staggered conformation that is a lower overall potential energy. And as we go to an eclipse setting, that is going to raise the energy. Notice that we're just using ethane in this case. And so with ethane, we will see that is 12 kilojoules per mole, okay? So all of the eclipsed are degenerate or the same energy, as well as all of those that are staggered. They are they are degenerate or they have the same energy. You can also do this with propane. In that case, the eclipse is 14 kilojoules per mole. And when they eclipse, you always get a CH3 in the same direction. And you all can prove this to yourselves. If you look at a model kit, I would highly encourage you to get out a model kit and play with that. Okay. Okay, now we're going to consider butane. So butane, remember, has 4 carbons in it. And when we start looking at butane, I'm going to begin by looking at what is a staggered conformation, and is specifically the anti-conformation. So the anti-conformation has a CH3 both above and below the plane. So notice that we have here, like if I'm looking at butane, I'm viewing this from the carbon on the second carbon and the third carbon. And so see how here, let me do it the other direction because I have it going the other direction where CH3 is going down in the front and CH3 is going up in the back. The way that I've represented this to you all, let me show you that way so that's a little bit easier to see. So see how my C2 and C3 are right here. Okay, so in front I have 2 H's and a CH3, and in the back I have 2 H's that are right here and right here, and a CH3 going back. Okay, you see it that way? Now, what I'm going to do is I'm going to keep the C2 locked. So I'm going to not move up here, okay? And let's play with this just a little bit and make sure that things are going to work okay. So I'm gonna lock that by putting my hand there. And if I go then and turn this slightly that way, then, nope, I need to turn it the other direction. That's what I was afraid of. Slightly in that way. Then what I have is, this is coming over to this side, okay? That is an eclipse of this hydrogen and this CH3. And of course, it also is an eclipse of this hydrogen and the CH3 here. And then as well as these two, okay? That is 16 kilojoules per mole that we have here. Now, the next thing that I'm going to do is rotate one more over. Now, this is a staggered conformation. But the staggered conformation has a CH3 down here and a CH3 over here. Now, I'm going to turn this so that you can see it from the other perspective. See how these are starting to get real close to each other? These CH3s are starting to get real close to each other. As you might imagine by seeing it from this perspective too, they almost are starting to overlap. And that's the reason why this is not as low of energy as we started off with over on this spot, okay? So this is a little bit higher here than what we started with at the anti-conformation. This is referred to as the gauche or gauche conformation. Gauche is the way I usually do it, or I've heard that referred to as. So again, I'm going to rotate over. When I rotate over, this puts my CH3s practically on top of each other in the back. And again, I'm going to show you that from the side. Look how these hydrogens are practically overlapping at that point. So is this higher energy? Yeah, it is. Of course it is. That makes sense, right? So that is 19 kilojoules per mole. And I can keep on going and rotating here. Make sure that that's in the right spot. There we go. And again, what we do is we hit another gauche conformation. So we've got these two that are kind of similarly as the beginning. They're kind of overlapping a little bit. And then we have another eclipse conformation. That would be like right there. So at this point, we're up here. Before finally going back to an anti-conformation. Now you may be asking yourself, why is it that we're going through all of this Newman projection stuff? Well, what we see is that this anti-conformation is by far the most stable. That's why most of the time you're going to find molecules in this type of format. Well, let me change this for you. Notice how we have a zigzag? That's the reason why we're drawing things in zigzag conformations, because that is what is much more stable. Okay. When you get to the overlapping eclipsed conformations, like what we have up here, right? You also, in addition to having torsional strain, we also have steric strain. What steric strain kind of means is that things are overlapping in the same space. So that's sort of what I was showing you with these things kind of running into each other. So that's where we start to get into more steric strain, okay? So that would be another issue that you're running into. Please make sure that you're looking at a model kit for these because it's going to make it so much easier. Run through these conformations yourself. You might need to pause here and there with what I've got and see if that's helpful to you as well. I hope that helps. Thanks.